The physical properties of alcohols. So most of the physical properties of an alcohol is based on the fact that they can hydrogen bond, right? I do have an oxygen. That oxygen is bonded to a hydrogen and then some carbon-based group, and then I have 2 lone pairs on it. Remember, to be able to hydrogen bond, I needed an OH, an NH, or an FH bond, and then I need a lone pair on that oxygen, hydrogen, or nitrogen. So we can form hydrogen bonds. It's also polar, so also dipole-dipole. Remember, polar molecules can form dipole-dipole interactions between them, so the partial positive end of one molecule is attracted to the partial negative end of a neighboring molecule, and vice versa. And then also they do have electrons, and those electrons are moving, and at any given point can be arranged unsymmetrically, so they do have London dispersion forces. Right, if I was to put some partial charges on here, I'm going to redraw my molecule here, actually showing a carbon. And then that carbon, of course, is bonded to different things. Hydrogen. This oxygen is partial negative, partial positive for carbon and for hydrogen. So it is a polar molecule. These can either be hydrogens or other carbons. But they are polar, so dipole-dipole, London dispersion forces, and then hydrogen bonds being the more important of the intermolecular forces that it can bond, or that it can form, excuse me. Steric factors do decrease hydrogen bonding. So steric factors decrease hydrogen bonding ability. So a primary alcohol, and we differentiate between primary alcohols, secondary alcohols, and tertiary, very similar to how we differentiated our alkyl halides, right? If the carbon, this time that's bonded to the hydroxyl group, not the halogen, is bonded to one other carbon, then it would be considered primary. So this carbon right here, right, this is the carbon that's bonded to the hydroxyl group, it's bonded to one other carbon group. This one here is secondary, right? This carbon is bonded to 2 other carbon groups. And then we could have a tertiary alcohol where that carbon that's bonded to the hydroxyl group is bonded to 3 other carbons. And as you guys know, as we increase the number of carbon groups, right, it becomes more sterically hindered. To form hydrogen bonds, the 2 molecules have to get close to each other, right? If I'm going to form connections between them, if I have a lot of steric things going on, right, they can only get so close, so hydrogen bonding is going to decrease. So this is my primary alcohol, my secondary alcohol, and my tertiary alcohol. And then in this way, we have better hydrogen bonding abilities. They can just get closer to each other, right? There's a lot of stuff going on, they can't get that close. So steric factors do decrease hydrogen bonding. So some trends for us. For compounds with the smaller molecular weight, higher molecular forces are going to have the higher boiling point and melting point. So for compounds with similar molecular weight, or molar mass, sorry, molar mass is the better term. So for compounds with similar, forgot some words down for you, similar molar masses, the higher the intermolecular forces, higher boiling point and melting point. So something like if I was just to do, let's say, propentane, and then I was to compare that to this ether, and then compare that to this alcohol, right? My alkane can only form London dispersion forces, right? Just carbon and hydrogen, so all my bonds are considered nonpolar. Ethers are polar. Oxygen is more electronegative than those carbons, so it can form London dispersion forces and dipole-dipole forces because it's polar. And then my alcohol, right, I have those lone pairs on there. The ether has lone pairs also, but it doesn't have a hydrogen bonded to it. So it's actually water soluble. I can form hydrogen bonds between my ether and water. So if we're talking about water solubility, which we will shortly, that's going to be soluble in water, slightly soluble depending on the size of those carbon groups, but not hydrogen bond to itself. The alcohol can hydrogen bond to itself. That's not a very good. Oop. My lone pairs look like a line. Don't draw lines for lone pairs. So this one, London dispersion forces, we just did this up above, dipole-dipole, and then hydrogen bonding to itself. So in this direction, higher melting points and boiling points. So my propanol compared to my ethyl methyl ether compared to my pentane, they're going to have higher melting point and boiling points as you go towards that alcohol. So let's add an example where we were comparing a tertiary to a secondary to a primary alcohol. Right? Remember we said as the amount of steric hindrance increases, they cannot get quite as close to each other. So hydrogen bonds are going to decrease, right? The more steric hindrance you have, or its hydrogen bonding ability, we should say. Which means as I go from tertiary to secondary to primary, we're going to have a higher boiling point. Water solubility. And we did talk about this earlier in the semester. We had a rule that said for an organic compound to be soluble in water, it needed to have at least one group that can hydrogen bond with water for every 5 carbons. So for alcohols, so ROH, ethers, ROR, right? Those can form hydrogen bonds because I have lone pairs in that oxygen. My epoxide can also form hydrogen bonds with water because it has those lone pairs on oxygen, right? They're forming the hydrogen bond to the hydrogen that's on water. The ether and the epoxide can't hydrogen bond to themselves, but they can hydrogen bond to water. So for these guys, if they have less than or equal to 5 carbons per every group that can hydrogen bond with water, they are water soluble. And what I mean by every hydrogen bonding group, I can have more than one hydroxyl group on an alcohol. So if I had 2 hydroxyl groups, then I could have 10 carbons, right? We could double that number. So an example, if I was to do this, I have 1 hydroxyl group, so 1 group that can hydrogen bond with water, but I have 1, 2, 1, sorry guys. You'd think I would have it worked out by now. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbons, so not water soluble. This one's probably slightly, but I would expect you to say not because it's, over that 5 carbon to 1 OH group ratio, so not water soluble. However, if I was to go and add another OH group onto it, right? Now I have 2 for every 6, so that 5 to 1 ratio, it's above that, so is, or below that, sorry, is water soluble. So count the number of carbons. I need 1 hydroxyl group for every 5 carbons for it to be water soluble. So this ether, 1, 2, 3, 4 carbons, it is water soluble. Here I have 1, 2, 3, 4, 5, 6, 7 carbons, not water soluble.